In statistics, maximum likelihood estimation is a method of estimating the parameters of a statistical model. When applied to a data set and given a statistical model, maximum likelihood estimation provides estimates for the model's parameters. The method of maximum likelihood corresponds to many well-known estimation methods in statistics. For example, one may be interested in the heights of adult female penguins, but be unable to measure the height of every single penguin in a population due to cost or time constraints. Assuming that the heights are normally distributed with some unknown mean and variance, the mean and variance can be estimated with MLE while only knowing the heights of some sample of the overall population. MLE would accomplish this by taking the mean and variance as parameters and finding particular parametric values that make the observed results the most probable. In general, for a fixed set of data and underlying statistical model, the method of maximum likelihood selects the set of values of the model parameters that maximizes the likelihood function. Intuitively, this maximizes the agreement of the selected model with the observed data, and for discrete random variables it indeed maximizes the probability of the observed data under the resulting distribution. Maximum likelihood estimation gives a unified approach to estimation, which is well defined in the case of the normal distribution and many other problems. However, in some complicated problems, difficulties do occur. In such problems, maximum likelihood estimators are unsuitable or do not exist. Principles: suppose there is a sample x1, x2, a euro, xn of n independent and identically distributed observations, coming from a distribution with an unknown probability density function fo, a. It is however surmised that the function fo belongs to a certain family of distributions a euro f, a euro I a euro, called the parametric model, so that fo equals f, a euro I0. The value I0 is unknown and is referred to as the true value of the parameter. It is desirable to find an estimator which would be as close to the true value I0 as possible. Both the observed variable psi and the parameter I can be vectors. To use the method of maximum likelihood, one first specifies the joint density function for all observations. For an independent and identically distributed sample, this joint density function is. Now we look at this function from a different perspective by considering the observed values x1, x2, a euro, xn to be fixed parameters of this function, whereas I will be the function's variable and allowed to vary freely. This function will be called the likelihood. Note denotes a separation between the two input arguments, and the vector-valued input. In practice it is often more convenient to work with a logarithm of the likelihood function, called the log likelihood, or the average log likelihood. The hat overall indicates that it is akin to some estimator. Indeed, estimates the expected log likelihood of a single observation in the model. The method of maximum likelihood estimates I0 by finding a value of I that maximizes. This method of estimation defines a maximum likelihood estimator of I0 a euro. A euro if any maximum exists. An MLE estimate is the same regardless of whether we maximize the likelihood or the log likelihood function, since log is a strictly monotonically increasing function. For many models, a maximum likelihood estimator can be found as an explicit function of the observed data x1, a euro, xn. For many other models, however, no closed-form solution to the maximization problem is known or available, and an MLE has to be found numerically using optimization methods. For some problems, there may be multiple estimates that maximize the likelihood. For other problems, no maximum likelihood estimate exists. In the exposition above, it is assumed that the data are independent and identically distributed. The method can be applied however to a broader setting, as long as it is possible to write the joint density function f, x1, a euro, xni, and its parameter I has a finite dimension which does not depend on the sample size n. In a simpler extension, an allowance can be made for data heterogeneity, so that the joint density is equal to f1, x1i, aaf2, x2i, aaaafn, xni. Put another way, we are now assuming that each observation's I comes from a random variable that has its own distribution function phi. In the more complicated case of time series models, the independence assumption may have to be dropped as well. A maximum likelihood estimator coincides with the most probable Bayesian estimator given a uniform prior distribution on the parameters. Indeed, the maximum a posteriori estimate is the parameter I that maximizes the probability of I given the data, given by Bayes' theorem. Where is the prior distribution for the parameter I and where is the probability of the data averaged over all parameters? Since the denominator is independent of I, the Bayesian estimator is obtained by maximizing with respect to I. If we further assume that the prior is a uniform distribution, the Bayesian estimator is obtained by maximizing the likelihood function. Thus the Bayesian estimator coincides with the maximum likelihood estimator for a uniform prior distribution. Properties: a maximum likelihood estimator is an extremum estimator obtained by maximizing, as a function of I, the objective function. This being the sample analog of the expected log likelihood, where this expectation is taken with respect to the true density. Maximum likelihood estimators have no optimum properties for finite samples, in the sense that other estimators have greater concentration around the true parameter value. However, like other estimation methods, maximum likelihood estimation possesses a number of attractive limiting properties. As the sample size increases to infinity, sequences of maximum likelihood estimators have these properties. Consistency: the sequence of MLEs converges in probability to the value being estimated. Asymptotic normality: as the sample size increases, the distribution of the MLE tends to the Gaussian distribution with mean and covariance matrix equal to the inverse of the Fisher information matrix. Efficiency: that is, it achieves the Kramer copyright Ra lower bound when the sample size tends to infinity. This means that no consistent estimator has lower asymptotic mean squared error than the MLE. Second-order efficiency after correction for bias. Consistency: under the conditions outlined below, the maximum likelihood estimator is consistent. The consistency means that having a sufficiently large number of observations n, it is possible to find the value of I0 with arbitrary precision. In mathematical terms, this means that as n goes to infinity, the estimator converges in probability to its true value. Under slightly stronger conditions, the estimator converges almost surely to. To establish consistency, the following conditions are sufficient. The dominance condition can be employed in the case of IID observations. In the non-IID case, the uniform convergence in probability can be checked by showing that the sequence is stochastically equicontinuous. If one wants to demonstrate that the ML estimator converges to I0 almost surely, then a stronger condition of uniform convergence almost surely has to be imposed. Asymptotic normality: maximum likelihood estimators can lack asymptotic normality and can be inconsistent if there is a failure of one of the below regularity conditions, estimate on boundary. Sometimes the maximum likelihood estimate lies on the boundary of the set of possible parameters, or the likelihood gets larger and larger as the parameter approaches the boundary. Standard asymptotic theory needs the assumption that the true parameter value lies away from the boundary. If we have enough data, the maximum likelihood estimate will keep away from the boundary too. But with smaller samples, the estimate can lie on the boundary. In such cases, the asymptotic theory clearly does not give a practically useful approximation. Examples here would be variance component models, where each component of variance, I2 florins, must satisfy the constraint I2 florins per ml 0 yen. Data boundary parameter dependent. For the theory to apply in a simple way, the set of data values which is positive probability should not depend on the unknown parameter. A simple example where such parameter dependence does hold is the case of estimating I from a set of independent identically distributed when the common distribution is uniform on the range. For estimation purposes, the relevant range of I is such that I cannot be less than the largest observation. Because the interval is not compact, there exists no maximum for the likelihood function. For any estimate of theta, there exists a greater estimate that also has greater likelihood. In contrast, the interval, 0, I, includes the endpoint I and is compact, in which case the maximum likelihood estimator exists. However, in this case, the maximum likelihood estimator is biased. Asymptotically, this maximum likelihood estimator is not normally distributed. Nuisance parameters. For maximum likelihood estimations, a model may have a number of nuisance parameters. For the asymptotic behavior outlined to hold, the number of nuisance parameters should not increase with the number of observations. A well-known example of this case is where observations occur as pairs, where the observations in each pair have a different mean but otherwise the observations are independent and normally distributed with a common variance. Here for 2n observations, there are n plus 1 parameters. It is well known that the maximum likelihood estimate for the variance does not converge to the true value of the variance. Increasing information. For the asymptotics to hold in cases where the assumption of independent identically distributed observations does not hold, a basic requirement is that the amount of information in the data increases indefinitely as the sample size increases. Such a requirement may not be met if either there is too much dependence in the data, or if new independent observations are subject to an increasing observation error. Some regularity conditions which ensure this behavior are: the first and second derivatives of the log likelihood function must be defined. The Fisher information matrix must not be zero, and must be continuous as a function of the parameter. The maximum likelihood estimator is consistent. Suppose that conditions for consistency of maximum likelihood estimator are satisfied, and I0 interior, I, f, xi, 0 and is twice continuously differentiable and I in some neighborhood n of I0. A super NAIF, xi, dxa, and a super NAIF, xi, dxa. I equals E, AILNF, xi0, AILNF, xi0, a euro squared exists and is non-singular. E, super NAILNF, xi, a. Then the maximum likelihood estimator has asymptotically normal distribution. Proof: skipping the technicalities, since the log likelihood function is differentiable, and I0 lies in the interior of the parameter set, in the maximum the first-order condition will be satisfied. When the log likelihood is twice differentiable, this expression can be expanded into a Taylor series around the point I equals I0. Where is some point intermediate between I0 and? From this expression we can derive that. Here the expression in square brackets converges in probability to H equals E, AAIIL A euro F, xi0, by the law of large numbers. The continuous mapping theorem ensures that the inverse of this expression also converges in probability, to Ha1. The second sum, by the central limit theorem, converges in distribution to a multivariate normal with mean 0 and variance matrix equal to the Fisher information I. Thus, applying Slutsky's theorem to the whole expression, we obtain that. Finally, the information equality guarantees that when the model is correctly specified, matrix H will be equal to the Fisher information I, so that the variance expression simplifies to just EO1. Functional invariance. The maximum likelihood estimator selects the parameter value which gives the observed data the largest possible probability. If the parameter consists of a number of components, then we define their separate maximum likelihood estimators, as the corresponding component of the MLE of the complete parameter. Consistent with this, if is the MLE for I, and if G, I, is any transformation of I, then the MLE for I plus or minus equals G, I, is by definition. It maximizes the so-called profile likelihood. The MLE is also invariant with respect to certain transformations of the data. If I equals AG, X, where G is 1-to-1 and does not depend on the parameters to be estimated, then the density functions satisfy. And hence the likelihood functions for X and Y differ only by a factor that does not depend on the model parameters. For example, the MLE parameters of the log normal distribution are the same as those of the normal distribution fitted to the logarithm of the data. Higher order properties. The standard asymptotics tells that the maximum likelihood estimator is a SHN consistent and asymptotically efficient, meaning that it reaches the Kramer copyright Ra bound. Whereas the Fisher information matrix. In particular, it means that the bias of the maximum likelihood estimator is equal to 0 up to the order Na1/2. However, when we consider the higher order terms and the expansion of the distribution of this estimator, it turns out that Imlayer's bias of order Na1. This bias is equal to where Einstein's summation convention over the repeating indices has been adopted. Jk denotes the J, kth component of the inverse Fisher information matrix EO1, and using these formulas it is possible to estimate the second-order bias of the maximum likelihood estimator, and correct for that bias by subtracting it. This estimator is unbiased up to the terms of order Na1, and is called the bias-corrected maximum likelihood estimator. This bias-corrected estimator is second-order efficient, meaning that it has minimal mean-squared error among all second-order bias-corrected estimators, up to the terms of the order Na2. It is possible to continue this process, that is to derive the third-order bias correction term, and so on. However, as was shown by Kano, the maximum likelihood estimator is not third-order efficient. Examples: discrete uniform distribution. Consider a case where n tickets numbered from 1 to n are placed in a box and 1 is selected at random. Thus, the sample size is 1. If n is unknown, then the maximum likelihood estimator of n is the number m on the drawn ticket. The expected value of the number m on the drawn ticket, and therefore the expected value of, is /2. As a result, with a sample size of 1, the maximum likelihood estimator for n will systematically underestimate n by /2. Discrete distribution, finite parameter space. Suppose one wishes to determine just how biased an unfair coin is. Call the probability of tossing a head P. The goal then becomes to determine P. Suppose the coin is tossed 80 times, that is, the sample might be something like x1 equals h, x2 equals a t, a euro, x80 equals a t, and the count of the number of heads h is observed. The probability of tossing tails is 1 AAP. Suppose the outcome is 49 heads and 31 tails, and suppose the coin was taken from a box containing 3 coins, one which gives heads with probability par equals a 1/3, one which gives heads with probability par equals a 1/2 and another which gives heads with probability par equals a 2/3. The coins have lost their labels, so which one it was is unknown. Using maximum likelihood estimation, the coin that has the largest likelihood can be found, given the data that were observed. By using the probability mass function of the binomial distribution with sample size equal to 80, number successes equal to 49 but different values of p, the likelihood function takes one of 3 values. The likelihood is maximized when par equals a 2/3, and so this is the maximum likelihood estimate for a p. Discrete distribution, continuous parameter space. Now suppose that there was only one coin but its p could have been any value 0 per mil currency pa per mil 1 currency. The likelihood function to be maximized is, and the maximization is over all possible values 0 per mil currency pa per mil 1 currency. One way to maximize this function is by differentiating with respect to p in setting to 0, which has solutions par equals a0, par equals a1, and pi equals a 49/80. The solution which maximizes the likelihood is clearly par equals a 49/80. Thus the maximum likelihood estimator for p is 49/80. This result is easily generalized by substituting a letter such as t in the place of 49 to represent the observed number of successes of our Bernoulli trials, and a letter such as n in the place of 80 to represent the number of Bernoulli trials. Exactly the same calculation yields the maximum likelihood estimator tar/an for any sequence of n Bernoulli trials resulting in t successes. Continuous distribution, continuous parameter space, for the normal distribution which has probability density function. The corresponding probability density function for a sample of n independent identically distributed normal random variables is, or more conveniently, where is the sample mean? This family of distributions has 2 parameters, ia equals a, I1/4, ai florin, So we maximize the likelihood over both parameters simultaneously, or if possible, individually. Since the logarithm is a continuous strictly increasing function over the range of the likelihood, the values which maximize the likelihood will also maximize its logarithm. Since maximizing the logarithm often requires simpler algebra, it is the logarithm which is maximized below, which is solved by. This is indeed the maximum of the function since it is the only turning point in I1/4 and the second derivative is strictly less than 0. Its expectation value is equal to the parameter I1/4 of the given distribution, which means that the maximum likelihood estimator is unbiased. Similarly, we differentiate the log likelihood with respect to I florin and equate to 0, which is solved by inserting. We obtain. To calculate its expected value, it is convenient to rewrite the expression in terms of zero mean random variables. Expressing the estimate in these variables yields. Simplifying the expression above, utilizing the facts that and, allows us to obtain. This means that the estimator is biased. However, is consistent. Formally we say that the maximum likelihood estimator for is. In this case the MLEs could be obtained individually. In general this may not be the case, and the MLEs would have to be obtained simultaneously. Non-independent variables, it may be the case that variables are correlated, that is, not independent. Two random variables x and y are independent only if their joint probability density function is the product of the individual probability density functions, that is. Suppose one constructs an order n Gaussian vector out of random variables, where each variable has means given by. Furthermore, let the covariance matrix be denoted by. The joint probability density function of these n random variables is then given by. In the two-variable case, the joint probability density function is given by. In this and other cases where a joint density function exists, the likelihood function is defined as above, in the section principles, using this density. Iterative procedures, consider problems where both states and parameters such as required to be estimated. Iterative procedures such as expectation maximization algorithms may be used to solve joint state parameter estimation problems. For example, suppose that n samples of state estimates together with a sample mean have been calculated by either a minimum variance Kalman filter or a minimum variance smoother using a previous variance estimate. Then the next variance iterate may be obtained from the maximum likelihood estimate calculation. The convergence of MLEs within filtering and smoothing M algorithms are studied in applications. Maximum likelihood estimation is used for a wide range of statistical models, including linear models and generalized linear models. Exploratory and confirmatory factor analysis. Structural equation modeling. Many situations in the context of hypothesis testing and confidence interval formation. Discrete choice models. Curve fitting. These uses arise across applications in widespread set of fields, including communication systems, psychometrics, econometrics, time delay of arrival and acoustic or electromagnetic detection, data modeling in nuclear and particle physics, magnetic resonance imaging, computational phylogenetics, origin destination and path choice modeling in transport networks, geographical satellite image classification. History. Maximum likelihood estimation was recommended, analyzed and vastly popularized by R. A. Fisher between 1912 and 1922. Reviews of the development of maximum likelihood have been provided by a number of authors. Much of the theory of maximum likelihood estimation was first developed for Bayesian statistics, and then simplified by later authors. See also. Other estimation methods. Generalized method of moments are methods related to the likelihood equation in maximum likelihood estimation. Estimator, an approach used in robust statistics. Maximum a posteriori estimator, for a contrast in the way to calculate estimators when prior knowledge is postulated. Maximum spacing estimation, a related method that is more robust in many situations. Method of moments, another popular method for finding parameters of distributions. Method of support, a variation of the maximum likelihood technique. Minimum distance estimation, quasi-maximum likelihood estimator, an MLE estimator that is misspecified, but still consistent. Restricted maximum likelihood, a variation using a likelihood function calculated from a transformed set of data. Related concepts. The BHHH algorithm is a nonlinear optimization algorithm that is popular for maximum likelihood estimations. Extremum estimator, a more general class of estimators to which MLE belongs. Fisher information matrix, its relationship to covariance matrix of ML estimates. Likelihood function, a description on what likelihood functions are. Mean squared error, a measure of how good an estimator of a distributional parameter is. The Rho-Blackwell theorem, a result which yields a process for finding the best possible unbiased estimator. The MLE is often a good starting place for the process. Sufficient statistic, a function of the data through which the MLE will depend on the data. References. Further reading. External links, Haswinkel, Michiel, ed., Maximum Likelihood Method, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Maximum Likelihood Estimation Primer, Implementing MLE for Your Own Likelihood Function Using R, a Selection of Likelihood Functions in R, Tutorial on Maximum Likelihood Estimation. Journal of Mathematical Psychology. Cite Searx, 10.1.1.74.671a.